Welcome back. In part 1, we looked at the intuition of embeddings, how we turn words into points in space so that king and queen end up next to each other. But we glossed over the mechanics. We treated the neural network like a magic box. Today, we break the box open. We're going to look at the specific architecture of Word2Vec. We're going to calculate the dot products, derive the loss function, and learn the specific mathematical trick negative sampling that makes training on billions of words actually possible. So let's do the math. First, the architecture. We're going to build a shallow neural network. We start with a specific goal. We're going to force the computer to solve a fake task, let's say. We feed it a word like great, and we ask it to predict which word appears near it in a sentence, like film. So great film. We don't actually care if it gets the prediction right. We care about the weights inside the hidden layer that it learns while trying to solve this puzzle. This architecture is called the skip graph. Okay, let's now trace the data. Our input is one hot vector. It's a list of zeros with a single one at the index of great. We saw this in the previous video. We multiply this vector by our weight matrix, W. Now, here is the most critical mathematical detail that most beginners miss. There is no activation function here, no ReLU, no sigmoid, nothing, because the input is just zeros and a single one. Multiplying it by the matrix is mathematically identical to just grabbing a specific row. If grade is word number 452, we just grab the row number 452. This layer acts as a lookup table, let's say. Okay, so now things get interesting. In the math of the Word2Vec, every word actually has two different vector representations. The first, we have the center vector, which we call V. We use this when the word is the input, like great. We have second, we have the this context vector, which we call U. We use this when the word is the target we're trying to predict, like film. During training, we're constantly trying to match the center vector of the input to the context vector of the target. So how does this neural network know if great and film match? It calculates a score using the dot product. We take the vector for great and the vector for film, multiply their elements and sum them up. If the vectors point in the same direction, the dot product is large positive number. If they point in the opposite directions, it's negative. This single number is our logit, or the row score. So we get a score, let's say 2.0. We need to turn that into probability so we can calculate error. Traditionally, we use the Softmax function, but we have a massive problem. If you look at the denominator of the Softmax equation or function, to calculate this probability for film, we have to divide by the sum of scores for every other word in the dictionary. Let's say we have 3 million words in our vocabulary. We have to calculate 3 million dot products just to do one single update. That is computationally impossible or very heavy. So we come up with a solution called negative sampling. It's like a cheat. we use a technique called negative sampling. So instead of calculating the probability against the entire universe of words or the dictionary, we turn this into a simple binary classification problem. We tell the network, I want you to give a high probability to this real pair, great film, and I want you to give a low probability to these five random noise pairs like great banana, great table. We ignore the millions of other words. We just focus on these few. And now, because we changed the problem for pick the best word to um, is this specific pair real or fake, we stop using the softmax. And we now switch to the sigmoid function. So this squashes our dot product into a number between 0 and 1. For great film, we want a high probability close to 1, as it is the case in this demonstration. For great banana, we want a probability close to 0. This leads us to our final objective function, or the loss function. We use negative log likelihood. It may look scary, but it's very simple. We just take the log of the probability of the positive pairs. We want this to be high, and then we add the logs of the probabilities of the negative pairs. We want these to be low. The training process is just adjusting the weights to maximize the score of the real pairs and minimize the score of the random pairs. So push the probability of real data to 1 and then the random noise to 0. Now we have the back propagation where we update the gradient. We will calculate the error and send it backward through the network. Mathematically speaking, this updates the vector coordinates. The vector for grade is physically nudged closer to fill. The vector for grade is pushed away from banana. So it should go closer to film and further away from banana. We repeat this for millions, maybe billions of sentences, and the vector organize themselves into a beautiful map that we saw in the first part. So briefly, there are two ways to structure this training. I just described the skipgram, where we use the center word grade to predict the context film. This works very well for the rare words. The alternative is the continuous bag of words. Here we take the average of all context words, like the film was, and try to predict the center word grade. It's faster, but skipgram is often more precise. And now once the training is finished, we have these two matrices, so the center vector and the context vector. What do? We throw away the context matrix. It was just a tool to help us learn. We keep the center matrix. So this is the center matrix. It's an error, and this is the context matrix. We throw this away. We keep this. The the rows of this matrix are our embeddings. If you download a pre-trained model like Word2Vec, Glove, you are just downloading this saved matrix. And now, because we build this whole system on linear algebra, simple dot products and additions, the resulting space retains linear relationships. This is why the famous algebra works, like vector of king minus man plus woman equals approximately, of course, to the vector queen. So we didn't program this rule, obviously. It merged naturally because the math of gender and the royalty, whether it's king or queen, are consistent across the entire dataset. So now that we have the intuition and the math part, it's time to get into the coding. In the next video, we're going to fire up a Jupyter notebook, and we're going to build this entire architecture, the lookup table, the dot products, and the training loop from scratch in Python. So until then, please subscribe and have a nice day.